Well, hello, everybody. My name is Brian Sherick. I'm the Global Vice President for Sales here at Flow International, and I want to welcome you to this presentation. And we're going to focus on 3D water jet cutting, the next dimension, we called it. So hopefully you're excited to be here. I'm excited to give the presentation to you. I'll take you through kind of a wide variety of topics, but we're going to really narrow down on the 3D side of the water jet cutting technology as we get going here. So let's go ahead and get started. So as engineering advances, so do the complexities in materials and part geometries. So from the early days of water jet cutting, boy, things have changed a ton. And it's because of these items here. You know, engineering is getting more and more advanced. Materials are becoming, certainly different than they were, 20 plus years ago. And part geometries are becoming more complex. And 5-axis cutting is becoming a real requirement for nearly everybody that has water jet, it seems like these days. So let's get into what those challenges and solutions look like. So let's start with, why consider a water jet at all in the first place? Let's kind of start from the beginning. And the answer that always jumps out to the top when that question is asked is unmatched versatility. We literally have a technology in water jet cutting that can cut any material type, from metals, which is the most common, application for water jet cutting, but composites are wonderful for water jet, stone and tile. A lot of food products are cut with pure water. Obviously, we don't put the garnet sand abrasive in there to cut foods, but a lot of food products are cut with water. Glass, paper products, you can stack materials, you can cut very thick materials because it's an erosion process. So it's a speed question, but it'll cut very, very thick. Precision cutting for microelectronics and the like. And then finally, bevel cutting. So when you talk about versatility, because it's a cold cutting process, the material types are literally unmatched. There's really nothing that won't erode over time. So it's a speed question. So that's the basic answer to why water jet. Now, they're really an ideal choice for just about any manufacturing organization that wants to reduce costs, improve efficiencies, and this kind of circular graph on the side here. Water jets are typically known to be very easy to operate in comparison to the machine tool world. They're relatively simple to program and operate, and we'll touch on that as we go through this. They're very quick to set up. There's not a whole lot of intricate, detailed fixturing that's typically required. There's always exceptions to these rules. So I'm sure that people out there have applications and jobs that require advanced fixturing, but as a general comment, fixturing and setup is a relatively simple thing on a water jet. We talked about the versatility of material types and then high quality part production. There are applications where you'll near net cut and then finish machine something, but oftentimes on a water jet, it's a finished product right off the jet. So very high quality part production. So let's start with some historical challenges before we jump right into the solution for 3D cutting and 5-axis solutions. I think it's important to understand some of the issues that have to be addressed or challenges that have to be solved before you can really do that. This image on the screen right here is a pretty good visual of one of the very basic challenges of a water jet. It's a non-contact cutting process. So what this image is showing you is imagine the cutting head moving from left to right across the screen. And you'll see that white line going through that acrylic material. And notice the entry point at the top where it's leaving the cutting head is at a different point than at the bottom where it's exiting the material. We call that stream lag. And that's an issue. We want to cut super accurate, smooth cut parts. And when you have that stream lag, you have to account for that. So along the bottom here, it kind of highlights these things. Water jets have a natural taper. Taper was commonly in this, 10, 15, 20 thou range. A little bit different than stream lag. We're going to look at taper as well, but there's a V-shaped cut, an angle to the part that we have to address. And then there's the stream lag that I just described, and you're going to see a video of this here in a second of this exact part with it moving across the screen. And so being able to predict those and solve those challenges is really important, even in 2D, especially before you get to 3D. So let's flip the page here and watch the video. So notice how slow it's moving here. And you notice there's not much deviation between where it's exiting the bottom and entering the top. This jet, this cutting head, is going to start speeding up as it moves from left to right. And try to notice here that that lag becomes more and more significant as we increase the linear travel speed of the machine. So you see it really starting to lag behind here. And it's going to create a rougher edge. You're going to have striations in the material. Now it's really lagging behind. And imagine for a second, see how it caught back up as the jet stopped? Imagine now that's in a straight line. If I was making a 90-degree corner or cutting at an arc with that non-contact cutting tool and this stream lag, I could have a less than desirable part for sure if I didn't address those issues. So here's another video that I want to show you that talks about the taper specifically and some of the other challenges. Again, I'm going to pause this video a couple of times. Right there, you'll see that stream lag. We just looked at that in detail. That's something we got to deal with. In addition to stream lag is this V-shaped taper. So as this jet is coming either towards us or away from us in this diagram, you see that V of the material. So I have an unwanted angle on the edge that I'm keeping. I'm trying to cut a perfectly vertical cut here. If I know what that V is, I can compensate for that, which is what we're going to do here in a minute. You'll see that solution. But if we don't, you'll see I've got a problem. I've got a non-vertical cut here. This is not perfectly straight. And as I made a 90-degree turn on the bottom of my material, that stream lag washed out into the part that I wanted to cut. So I have a damaged area of the part that I want to cut. I can solve that by slowing way down into that corner, or I can compensate for it through software and mechanical means, which is what Dynamic Waterjet does. So this simulation is showing just that. It's showing Dynamic Waterjet modeling to address those major issues. The reason it's so important to understand all this before you go to three-dimensional cutting, you've got to be able to solve this in two-dimensional. And that's what that's doing. It's just showing a simulation of that slight articulation of the cutting head to transfer all that taper and scrap to the scrap side of the part so that the actual part you're keeping is vertical and accurate. See some more of this as we move on. So let's talk about these different cutting head solutions that you can use on a Waterjet machine to produce these parts. On your left is your standard Waterjet. So kind of the traditional basic technology of a vertically mounted cutting head on a machine that's moving in X and Y. And the only way to address those issues that we just went through is through linear travel speed. So if I want accurate and smooth and precision parts, I have to go slow. The next cutting head, as you move from left to right, is called Pivot Plus. This is bevel cutting technology. Now I've got a very simple 5-axis wrist that will articulate to allow me to cut bevels and angles. The third cutting head from there is called Dynamic Waterjet. We're going to see a video of that in a second, where we're going to compensate for taper for two-dimensional parts, but we want perfectly vertical, accurate cuts. And then on the far right is the technology where we really get into precision and 3D cutting called Dynamic XD. And those are kind of the 4 most common platforms. The 5th one that's not on the screen, by the way, would be water-only cutting. So for those food applications I mentioned earlier, and for soft materials, you actually can just use a very simple nozzle to cut with water only. These are all for abrasive jet cutting. So let's talk about this taper in a little bit more detail. Tolerances typically went from that 5 to 10 to 15 thou range without taper compensation, to where now with dynamic we can do things in that 3 thou range or even tighter if you really control all the variables. And then speed increased 2 to 4 times when we came up with a way to compensate for these issues we're talking about. Because if you think about it, if I want an accurate cut, I got to go very, very slow with that traditional Waterjet. Well, now I can electronically, or I can compensate for those through software and hardware and go much faster to get the same accuracy or even tighter accuracy. And then obviously that reduces your cost, so parts become much cheaper to produce. And then I believe we have a video here. Oh, sorry about that. So here's the Dynamic Waterjet in action. Click the video screen. And all you're going to really see here is while it pierces through the material, you'll see a little white puff of steam from the water. But as you watch the head, just notice the very small articulation of those motors and that wrist. And this is cutting a two-dimensional vertical cut, but it's removing all that taper and putting it on the scrap side of the part. That's very fundamental to being able to cut accurate parts. So remove this. Challenges solved by innovative engineering, software solutions, and then obviously the hardware that you need in the cutting head to be able to articulate and control that movement. As we move to 3D cutting solutions now that we kind of understand those basic challenges, think about the complexities that get added to the equation. So what makes 3D cutting even more challenging? So now we have varying degrees of angles on one part. There's a head rotation and a change of feed rate as we do that, as we're cutting at angles now instead of just vertical. And then we have a thickness variation during the cut. So as we tilt the cutting head through a piece of material, that cut becomes thicker because it's going through more material. We've really added a lot of variables to the equation here, which all need to be accounted for in order to cut not only an angled cut, but an accurately angled 3D cut. And I'll start by telling you, 3D cutting using Waterjet is not new. We've been producing systems like this massive system here, cutting an aerostructures part for years. 30 plus years we've been building advanced 5-axis Waterjet cutting solutions, and we do a ton of this in aerospace and in automotive and other applications that use articulated arm robots and big gantry systems like this one with CNC controls. There's a couple of major challenges to making this mainstream, or were challenges, and that was the cost of these systems are obviously highly engineered, custom solutions. They're very expensive, and they're frankly not easy to program. This is a pretty advanced application that requires pretty advanced programming capabilities. Well, we've changed that. We've simplified all of that, which we're going to talk about here in a second. First of all, what's the difference between bevel cutting and 3D using a solid model? A bevel cut is where I just take a flat image and I tilt the cutting head at a particular angle, and the entire edge will have a constant thickness because I'm just at that constant angle. The wrist will set and hold a set position. It won't taper control. It's just going to cut a standard bevel cut. Stream behaves just like it does in 2D. It's just the head is tilted at an angle. It's very simple. That's bevel cutting. A bevel machine can't cut a 3D part because of what we just talked about there. A 3D machine can cut a simple bevel. Kind of an obvious statement, but important to understand as you're looking at Waterjet technology. It's two very different things. So let's look at what that means. So for bevel cutting, we've gone from that huge system that we just looked at a second ago, which is multi-million-dollar solution, to now a very affordable way for just about any job shop or fabrication facility to get into 5-axis cutting, to where you can do this bevel cutting. The head pictured here, entry-level beveling and contouring capability, previously only available on advanced machines. Now it's very affordable and easy to use. Ideal for simple beveled edges. Weld prep is a very common application for this technology. And then thick 3D parts that require lower accuracy, but really usually pre-machined removal of material for finished machining is another common application for something like this. So most basic bevel cutting, what to look for. You want a small compact envelope. This would be a low-cost, small envelope type system. 5-axis cutting with taper control is still really, really important. So even though it's not the most advanced, expensive machine that we build, we still need to be able to take care of that taper and stream lag, those issues we looked at the beginning of the presentation here. This technology, typically is up to 60 degrees of angle capability from vertical. If vertical is 0, we want to be able to go 60 degrees from vertical. Low profile mounting is important for your fixturing and clamps, so that you're not running into things with a 5-axis wrist. You want to look for low profile mounting. And then simplified design for abrasive feed and cable routing. You can imagine now that we have a wrist that rotates and moves in 5 axes, we've got to account for that. That's different than just having a vertically mounted, hard mounted cutting head to the machine. And then contour following. Contour following becomes more and more critical as you start to cut things at an angle. If you're cutting everything vertically, the standoff distance is not nearly as critical as if you're cutting things at an angle. And we're going to go through the details on that in a second. Here's the Pivot Plus head that we just looked at doing a 5-axis cut. You can see it dancing around the material, and it's much more angle than just that dynamic water jet we looked at earlier, where it was doing a 2D part and vertically cutting accurately. This is actually cutting at an angle. It's actually cutting, I think, a piece of granite or some sort of solid surface for, that looks like metal there, but this is a granite piece here. The stone fabrication market is a hot industry that utilizes this technology right now, but you can see the Pivot Plus in action a little bit there. So in summary on that, it's ideal for fabricators cutting a lot of weld prep and bevels, the stone customers I just talked about for their mitered edges, general fabrication customers that want high value but don't want to break the bank and spend the kind of money on those big aerostructure type machines. And then, like I mentioned, rough cutting parts before any kind of secondary operation. And again, we talked about kind of both sides of that. Sometimes you can cut a finished part on a water jet, and sometimes it makes a lot of sense to near net cut something, remove as much as you can, and then secondary finish it on a machining center. So that's what that technology is really ideal for. Now look at the next level. The next level is where you get into true 3D with taper control, and this is XD technology. So it's multi-axis cutting. It's again, the 60 degrees of motion with full taper control, but it's a much more advanced, accurate, rigid structure in the cutting head system itself. And you'll see some of that in action here in a second. So the head automatically compensates via software to eliminate that taper in the 3D motion that it's cutting. And it's got to take into account the speed that it's moving in the linear direction, the thickness of the material, the geometry it's cutting, and the angle. So the math behind the algorithms in the software get pretty complicated, which again goes back to why the technology, a decade plus ago was only for those advanced solutions. It's now becoming very, very common. This is a really good image of the type of part that an XD head will do. So you got kind of multiple things going on here. If you look in the top left, you see the head tilted over at a pretty severe angle there. And it's a great example of the simple fixturing I'm talking about. So we've got some very basic low profile clamps holding the piece in place. And it's imparting multiple angles around the different sides of this cut part. On the bottom left, you'll notice a K bevel. And then on the right side of that bottom left image, you'll see a very, very sharp, almost knife blade edge in the middle of the geometry. On the top right, you see a pretty intricate cutout there where there's a lot of articulation needed in the XD wrist. And then the kind of overhead view of the part on the bottom right. So it's a really good example of a true XD application where all of these things come into play. Here's the XD head in motion, cutting a part like that. And what we're going to talk about in a second is controlling that height variation. As my height changes and I'm at an angle, I got an issue if I don't account for that. But you can kind of see the XD head in action here. And it mentions the compass multi-axis contour follower we'll look at in detail. There's the head laying over at a pretty good angle. That's real-time cutting speed, cutting through. I think that's like a 1/2-inch stainless that we're cutting there. But again, it'll do any material at any thickness. It's a question of speed and accuracy. So here's a software is key. I think it goes without saying that all of these variables we're talking about, for a programmer to have the knowledge and experience and be a water jet expert isn't realistic, especially if you're going to do multiple applications and different materials and thicknesses. It's just not realistic to be able to program all of that through G code and to have that knowledge built in. So software modeling through Flow Expert is really, really important to be able to make this a usable, technology. Here's a little recorded demonstration of the Flow expert in action where somebody's drawing a part. So you're actually doing the CAD work here. Of course, you can import the CAD image from a multitude of different CAD packages, or you can use this as your CAD package itself and do your creation right here. So we've drawn a square here. We're putting some holes in it, and you'll see as we go through this, the key factor is that we're not just going to impart an angle to a flat stock piece of geometry. We're not going to take a DXF image and just put an angle to it. Right there, we just pulled the image to a true 3D thickness. We want to be able to actually determine the angles in true 3 dimension, and we need to know the thickness to do that. Here it's putting a little radius on that corner, and then you'll see the angle. It's going to put on a weld prep edge right here, enters 45 degrees. Now we've got an angled edge, another angled edge on this side. And then, so there's your geometry. And then to toolpath this, it's a very simple function. It's basically an automated function. And you see there, it put in all of its start and stop points for each of those holes. It traveled, it traversed with the jet off in between each hole. It did not travel over a cut area, which is important. And then we have a finished part. And it's done. It's sitting on export. And so the process would be now we export this 3-dimensional file over to the control software of the machine itself and cut the part, as you've seen in some of those different videos. So again, that looks really simple because it is, and it didn't used to be. So to be able to do 5-axis cutting in the old days of Waterjet was very, very complicated, but we've really come a long ways in the software side of things. Another video showing this in action. I'm going to pause here for a second. What we're really going to show here is how to take care of how to take care of the standoff distance issue. So like I mentioned earlier, the distance from the material we're cutting becomes very, very important if we're going to cut at an angle. And that's what this little demonstration is going to show you. And that's what the technology called Compass takes care of. I'll kind of talk through this and pause the video a couple of times. There's the head at a pretty significant angle, and that standoff distance is going to change. Well, if it changes, it's going to have a huge impact on the accuracy of my cut, because it's not going to enter the material where I want it to enter. You'll see it right here. So contour followers exist to help solve that problem. That's not unknown. And in 2D on flat material, they all work. It's pretty straightforward. What happens when your work surface isn't flat? Well, now we have a problem, because now we have air caused that is not, because it's not perpendicular to the material we're cutting anymore. You'll see in this demonstration here how we have managed to kind of deal with that. Right there, it's showing where the real problem is. If I'm only compensating based on the leading edge of my cut, where the ring is touching the material, I'm not perpendicular to the surface I'm cutting. So I'm not accurately maintaining my standoff distance. And the bigger that angle becomes, the bigger that error. So Compass solves that problem because it actually rotates and gimbals along the surface of the material, which you can kind of see it doing there. That red piece or that yellow piece actually rotates along the material. That's a big factor in 5-axis, cutting super high accurate parts in 5-axis anyway. So let's talk about a real customer application. I think this is a pretty good example of one of our customers in New York City. They're a boiler tube sheet manufacturer. So they'd been milling parts. They were doing 1 to 2 sheets a week of the parts that they were producing. These are pretty big, lots of cut holes in these parts. With the addition of their 94K XD 5-axis wrist with Compass height sensing capability, it reduced their cycle times dramatically. They were holding great tolerance, 1 to 3 tolerance, and now they're cutting 1 to 2 sheets a day versus 1 to 2 sheets a week. So serious productivity gains by this particular application. Here's an interesting couple of quotes from this customer, from Jason at Steel Design Manufacturing. With the enhanced capabilities of Flow's 5-axis head, we've gone from not quoting 3D shapes to processing them as normal everyday items. That's something we hear all the time. We hear so many of our job shops or contract cutting facilities talking about, yeah, I really don't do any 5-axis cutting. I'm not sure I need it. That could be true. What we see all the time is somebody that invests in the technology says, wow, now it's become commonplace. Now that people know that I have the capability and the technology, it's become a standard offering, and it's not adding to the complexity of using the machine, because we've dealt with all that through the software that we've talked about. So anyway, I think that's a pretty common line that we hear a lot. So this customer ran their 5-axis head on a variety of materials up to 2-inch thick. You see the different A36, AR400, and 500, 304 stainless. And then machine shops are like we've talked about earlier, utilizing us to rough out blanks for them, and having the capability to add 3D cuts into their profile have really helped to remove more material and lower run times on their CNC machines. So again, whether you're cutting a finished part or a near net part that needs to be finished machined, that 3D capability, is a big advantage in a lot of those applications. So that's just one particular customer and some feedback from them. Talk about the different industries that use a lot of 5-axis, 3-dimensional type cutting solutions in Waterjet. Aerospace is a huge one. Aerospace has changed a little bit recently, but it's still a mainstay that uses a lot of 5-axis, 3-dimensional Waterjet cutting. The food applications we talked about, the space industry, it's a huge growing business that's utilizing Waterjet cutting in 3-dimensional for a lot of the advanced alloys and materials and composites and geometries that they need to produce. Architecture is a great industry for Waterjet. We talked about the countertop business, how it's kind of changed into these mitered cut edges, electronics, transportation, energy, manufacturing in general. And then automotive has been a mainstay that uses 3-dimensional, robotic trimming and cutting for a long time. So a very diverse, wide range of different applications in different industries that utilize this technology. We'll buzz through just a couple of those. The aerospace, military, and defense we talked about. Our architecture and construction for building materials. Automotive, your interior carpet cells, your headliners, your door panels, all that stuff is usually trimmed with a 5-axis robotic Waterjet on an articulated arm robot. A lot of electronics are being done because of the minimal kerf width of a Waterjet. So what we recommend in the industry is, if you think you have an application or you want to test a 3D application, I highly recommend you to get a test cut. You've got to see your real life application or potential applications, being done. How do you program the part? How difficult or easy is that? What does the cutting look like? What's the fixturing look like? All the things we've kind of talked about today in this presentation. You really need to do a test cut if you want to know all the facts. And so I highly encourage you to do that. So with that, I just want to thank everybody for coming and listening to the presentation. Please take advantage of this test cutting that I'm talking about. Get a quote on a machine, get a software demo. Make sure and come visit Flow at the booth at Fabtech. We're really excited to see everybody and be back in person soon. So thanks again. Appreciate your time.